Okay, this week we will look at simple linear regression with hypothesis tests and confidence intervals. We will also talk a little bit about binary variables or dummy variables, as well as the effects of heteroscedasticity. Remember also that you have a test next week, so you should be studying your quizzes to help you on the test. So first, let's ask what kinds of questions can we ask that would utilize a hypothesis test with regression? We have an example from our book that can help with this. An angry taxpayer disagrees that the student-to-teacher ratio is affecting the test scores. She does not want to pay higher taxes for more teachers because it will increase the already very high tax in California. So how can we determine if the angry taxpayer's accusation is true or false? We can test if there is any correlation between the two variables. To do this, we can test if the coefficient of our independent variable is 0. If it is 0, then the slope of the regression line would be 0, thus no variance is explained by the independent variable for that of the dependent variable. Thus, our object of interest is our beta 1 coefficient from the regression analysis. Beta 1 is the slope of the population regression line. Now, using our assumptions for successfully using regression, our sample should be IID, and there should be little or no outliers. This all comes back to the law of large numbers and the central limit theorem. Anyhow, back to our object of interest, beta 1. We have a large sample volume, and the sampling distribution is approximately normal, and if the distribution is normal, then we can run many of our statistical tests that we would like to. So beta 1 comes from a normal distribution. We can run the tests that we're interested in particular regression. Our objective is to test the hypothesis that beta 1 equals 0. Thus, the slope is 0 and there is no correlation between the two variables. We want to use a two-sided hypothesis test unless we have prior evidence about the direction of the hypothesis, which we very rarely do have that kind of evidence. Thus, we will make the alternative hypothesis that beta 1 does not equal 0. In general, to perform our hypothesis test, we will find our t-statistic, where t equals our estimator minus the hypothesized value divided by the standard error of that estimator. Fortunately, our hypothesized value is usually 0 because we are testing for a slope of 0. So to find the t-statistic, we take our beta 1 coefficient minus our hypothesized value of 0 and divide by the standard error. To calculate the standard error of beta 1 gets pretty complicated, and we're going to talk a little bit about this later. And I'm not going to make you do it by hand, as we will usually use software to calculate this value. So do not worry about memorizing the formula. So to summarize, our null hypothesis will be that beta 1, our independent variable's coefficient, and the slope of the regression line will be 0. Our alternative hypothesis will be that beta 1 does not equal 0. If our null hypothesis is found to be true, then the two variables will be uncorrelated. However, if we reject the null hypothesis, then some correlation may exist between the dependent and independent variables. We then find our t-statistic, and if that value is greater than 1.96, then we can reject the null hypothesis. So let's go to Excel and take a look so we can set this up. Your book uses a program called Stata, but we can do this in Excel. But because of the different programs, the numbers will be slightly different because of how the standard error is calculated. which we're going to talk a little bit about later in this presentation. So we have our California schools data, and what we want to find is determine if student to teacher ratio actually has an effect on average test score. So our null hypothesis is that the slope or the beta 1 coefficient for student to teacher ratio will be 0. That would prove the angry taxpayer's accusation. However, if it's not 0 and we can reject the null hypothesis, then there's some correlation between the variables, but it doesn't necessarily mean that student to teacher ratio is causing average test score. So it's pretty easy to calculate this out in Excel. If we do a regression, go to Data tab, Data Analysis, drop down to Regression, select our Y variable, which is our average test score, and our independent variable X, student to teacher ratio. We have labels. I'm going to output it onto this sheet, and we can run it. What we'll see clear is our beta 1 coefficient here is negative 2.27. I calculated out the standard error, but this is actually not the correct standard error. But it calculates the t statistic and the p-value based on that standard error. I'm going to tell you a little bit about this in a second. But based on this analysis, we have a p-value of very, very small, so we can reject the null hypothesis. So the next step we want to talk about is confidence intervals. Remember that a 95% confidence level means an interval that contains the true population value 95% of the time, and it is the set of points that we cannot reject the null hypothesis. Fortunately, creating a confidence interval for beta 1 is the same as the confidence interval for the mean. We take our beta 1 coefficient and add or subtract our significance value of 1.96, and we multiply that by the standard error. You can take a look in Excel and see that it will calculate the confidence interval for us. So confidence interval calculated here, but once again it is based on this standard error. So we can estimate a regression line and find estimators for the slope and intercept, here beta 1 and beta 0, under the assumption we have a large normally distributed sampling distribution. We can then use the information to do a hypothesis test about the slope value of beta 1. Really, we are trying to determine whether or not there is any correlation between the dependent and independent variables. Afterwards, we can calculate out our confidence interval. So we will talk about this more when we do logistic regression, but let's hint at it for now. Binary variables are variables that can only take on two values, 0 and 1. This can be for the dependent or independent variable, or both. Let's look at our California schools example. We want to create a dummy variable for the number of students in a class, where 20 or less equals 1, and all other values above 20 equal 0. Then we can test the effects of standardized class size. So far, we have beta 1 as a slope, but in this case, that does not make sense. I can show you how we can do this in Excel, though. So if we wanted to create a new dummy variable for less than 20 students, So let's put class size. We can use a formula. We can use an if formula. Go back to the top. So equals if this value is less than or equal to 20, it will be a 1, and otherwise it will be a 0. Now we've created a dummy variable that any value less than 20 will be a 1, and if it's greater than 20, it will be a 0. Now we could do our regression again. Change this to I'll put this up here. That's what our regression would look like using the dummy variable for class size. Now, how do we interpret that? The way we can interpret results is basically an easier way of doing a difference in means test. If you think about the California schools example, we are finding the mean test score of students 20 and below compared to the mean test score of students above 20. We can see here that if we run the regression, the coefficient is actually the difference of the means of the two groups. So if we were to find the mean average score of greater than 20 and the mean average score of, this one should be less than or equal to 20 and that one should be greater than or equal to 20. What we find is that the actual coefficient or beta 1 we get is the difference between those two averages. So it's really like finding a difference in means. What we find is that when we use a dummy variable or a binary regressor, that t-statistics and confidence intervals will be calculated out the same way, and that this is just another way to do a difference of means test. We will talk more about the usefulness of dummy variables when we get to multiple regression and logistic regression. So homoscedasticity means that the error variance is the same level at all levels of the variables. The alternative is called heteroscedasticity. This is more likely the case where the error variance has different effect at different levels of the variables. We've only learned how to calculate the standard error when the data is homoscedastic, and this is how Excel will calculate it. However, if our data is heteroscedastic, then we have to calculate out a more robust form of the standard error to take heteroscedasticity into play. So when we look at these standard errors, particularly this one, the standard error is falsely low. If we used robust standard error to account for heteroscedasticity, the standard error would be 0.52. So Excel gives a falsely low standard error, which is going to affect your t-statistic, your p-value, and your confidence intervals. So basically, if we have equal group variances, it's called homoscedasticity and is calculated out with a different formula than that of unequal group variances, which is heteroscedasticity. This shows what homoscedastic data is. At any point in X, the distribution of Y remains constant, as the variance does not depend on X. The Gauss-Markov theory was developed with ordinary least squares and proves that if the data is homoscedastic, hence why it's an assumption for running regression, then the ordinary least squares estimator is the best linear unbiased estimator, or BLUE. Basically, we're able to simplify the formula if the data is homoscedastic. So we have two forms of our standard errors. So those that are truly homoscedastic and our robust standard errors that work in either case. In Excel, we only have the homoscedastic standard errors. And what this leads to is that our t-values, standard errors, and confidence intervals are wrong. In fact, they will be too small, as evidenced when we used Excel. You can use other software like Stata that will give us robust standard errors, but Stata costs money. I can show you how to do it in the programming language R, but we will have to wait until we actually start using R because it involves running some extra functions. So hopefully that helps you understand why we use hypothesis testing with linear regression, as well as the effects of homoscedasticity and heteroscedasticity, and the use of a binary regressor or dummy variable.